In the last section, we studied the Gram-Schmidt process and QR factorization. Here we'll apply the QR factorization to find eigenvalues and eigenvectors. See the algorithm QR iteration for a square metric A, and in each iteration we make a QR factorization and multiply RQ to get new A, and from U, beginning with identity, we update by multiplying right side a Q metric. So that's quite simple. Once it is convergent, then the limit of A is T and limit of U is U. Okay, that's the output. From the algorithm, we can see this one. Now, AK is RK, QK. Now, Q is an orthogonal metric, so we multiply Q transpose, then that will become RK, and that is Q transpose AK. So we can get that one. So we have AK and AK minus 1 relationship. We apply this equation recursively to get this one. Here, AK is along with QK transpose QK, now AK minus 1. Apply one more time, then AK minus 1 will be written in this way, and continuously then we reach at A0. A0 is A. Now, once it is convergent, then this portion is UK. We updated here, and that will be UK transpose. So the limit of UK will be U, and we can reach that one. And limit of AK is T. So T equal U transpose AU. Now, so from this algorithm, we can get it. Now, we'll try to understand what they are. T is an upper triangular metric, and the diagonal will be eigenvalues of A, and U is an orthogonal metric, so that from this one, we can write in this way easily. And this decomposition is called the Schur decomposition of A. Okay, why it is a triangular metric? Let's see here. The limit of AK is T. Now, in this reverse multiplication, okay, R, okay, let's try to visualize the metric. R is upper triangle metric, and Q is orthogonal metric, which means that the columns are orthonormal. So length 1, but RK has only non-zero here. Below will be 0. Now in this product, row, column, but these are 0, so that the product will have a smaller value in this lower part. So this portion will converge to 0. So T must be upper triangular metric. Okay. Once A is symmetric, then T becomes diagonal metric of eigenvalues of A, and U is the collection of corresponding eigenvectors. If A is symmetric, then T also should be symmetric, but if a lower portion converges to 0, then simultaneously upper portion must be also converging to 0, so that it must be diagonal. Right? Let's see example. We have two matrices, A and B. A is not symmetric, but B is. We'll apply the QR algorithm, QR iteration, to find their sure decomposition. Okay. Now, okay. In one of the exercise problem, you'll work with a Python. Okay. For this is QR iteration here, and once A is given, we assign to be T, and U is the identity, and T is factorized QR, and then now update RQ, and here Q is multiplied to get the transformation metric updated. Okay. Below portion is for stopping. Right now, here, if change is larger than tolerance, 10 to the minus 5, it's stopped. But the change is measured from here, the T, the diagonal T is checked, and for the successive T, the diagonal changes less than the tolerance, then the iteration stops. Okay, this one is committed out, but now along with that one, we'll try to see how the off-diagonal entries are changing. Okay, we'll see later on. Okay, for two matrices, along with the QR iteration, we implement now call QR iteration.m, and here after QR iteration, it will be saved here T1 U1 iteration 1, and we try to cover the original metric and compare with the eigenvalues and eigenvectors. And also for the symmetric one, we do the same way. These are output. Okay, that is T1 U1 after 26 iteration, it converged. Now that one, and we try to recover the original metric as well recovered. And from eigenvalue computation, we see these are eigenvectors and these are eigenvalues. Let's see T metric and diagonal entry. So exactly the eigenvalues. This is not ordered, but here we have ordered eigenvalues. For symmetric case, and T must be upper triangular metric, and now because of symmetry, it must be diagonal metric. And these are eigenvalues, 6, 3, 1. And also in theory, this must be corresponding eigenvectors. After 28 iterations, it converged. And we try to recover the original metric. It's well recovered. And from eigenvalue computation, these are eigenvectors and these are eigenvalues. Again, same eigenvalues even though they are not ordered. But here, it is well ordered. And see the corresponding eigenvectors for 6. Okay, this is the eigenvector. For that 6, that is the eigenvector. They are the same, right? Okay. Now we'll see here convergence check. This is for non-symmetric case. This is symmetric case. And after each iteration, the AK are here produced. Let's see here. Okay, after one iteration, lower part is given in this way, and after second iteration, third iteration, fourth iteration, it becomes smaller, smaller, smaller. And so that after 8 iteration, you can see now almost 0. The reason is, major reason is from earlier I explained it, and RQ multiplication, this low portion is 0, and this metric product makes a smaller contribution because of this 0 and now that column. Row column computation will make smaller values, and because this portion is 0. Okay. Okay. For now the symmetric case, the convergence is here symmetric, and after each iteration the output must be symmetric. Now look at bottom portion and upper portion. They are converging the same way and symmetrically and becoming smaller, and then is now after 8 iteration it's quite small, but anyway symmetric. Okay, that's the one computation result, and this is the end of the section. Thank you.